Welcome to the deep dive.
Okay, so you've given us quite a stack of material here. It really covers a lot. Um, the early ideas about AI, the math behind it, how machines learn, robotics, even language processing.
That's right. It's quite a journey through the field.
So think of this as, well, your personalized tour through all that. Our mission today,
Hmm.
to kind of navigate this landscape you've laid out, hitting the key ideas, and maybe tracing how our picture of intelligent machines has changed over time.
Exactly. We're not just summarizing. We want to focus on those fundamental bits, knowledge representation, reasoning, learning, interaction, to really get a sense of AI's journey and maybe even where it's heading.
Okay, let's start unpacking that. The whole idea of making machines intelligent. It's
Yeah.
been around forever, hasn't it? And the sources you gave us, they start with that really thorny question, can a machine think?
Right. Which can get very philosophical very quickly.
Yeah, so instead of getting stuck there, Alan Turing came up with something pretty practical, didn't he? The Turing test. It was really quite clever. It shifts the goalposts. Forget defining thinking. The test just asks, can a human, just by typing back and forth, tell if they're talking to a computer or another person?
Mm-hmm.
If the computer can fool the interrogator often enough, well, it's acting intelligently, at least in that specific context, functionally intelligent.
Right. And to actually pull that off, to be convincing, the material highlights some pretty major capabilities a machine would need.
Oh, definitely.
Things like, understanding and using human language, having a ton of world knowledge,
Yeah, common sense knowledge, which is tricky.
and being able to reason, solve problems, and crucially, the ability to learn new stuff as it goes. That's a tall order.
It really is.
Yeah.
And that leads us neatly into the mathematical and logical bedrock that AI is built on. If you want machines to reason properly, you need a solid framework.
You need the math.
You need the math.
Yeah.
Logic, probability, computation theories are all essential pieces.
Absolutely. And the sources, they trace logic way back. Greece, India, China. But the real mathematical engine starts with George Boole, right? Boolean logic.
Yep, turning logic into algebra, essentially.
And then Gottlob Frege steps it up with first-order logic. That lets you talk about objects and how they relate to each other.
Exactly, which is huge for representing knowledge.
Yeah.
And here's a really key connection. This logic wasn't just theory. It directly fed into the work of Gödel and Turing.
The guys who basically defined what computation is.
Precisely. So first-order logic gave us the language, and Gödel and Turing helped define the limits and possibilities of computing with it.
Wow, okay.
And building on that, you also get things like decision theory, how a single agent makes choices when things are uncertain.
Like probabilities?
Kind of, yeah. And game theory, which is about multiple agents interacting. How do they make decisions when their outcomes depend on each other?
Game theory has some weird results, doesn't it? Like sometimes the smartest thing to do is to be unpredictable. Random, even.
That's one of the fascinating insights, yeah. And that idea definitely carries over into AI research on multi-agent systems, trying to get different AIs or AIs in humans to cooperate or compete effectively.
Okay, interesting. So let's jump to when AI starts becoming its own thing.
Hmm.
The sources point to 1943 McCulloch and Pitts. That seems pretty early.
It is, yeah. They came up with the first sort of computational models of neurons, artificial neurons.
Okay, so what went into that? The sources mention a few things.
Well, they were looking at actual brain biology, how neurons seem to work.
Uh-huh.
And they combined that with the formal logic of Russell and Whitehead and, again, Turing's ideas about computation.
So they built this model,
Mhm.
artificial neurons that were either on or off, based on signals from others?
Pretty much, yeah. Simple threshold logic. If enough inputs are active, the neuron fires.
And what was so important about that simple model?
What was amazing is they showed networks of these things could theoretically compute anything computable by a Turing machine.
Anything.
And they could implement basic logic A and D, or not T. They even hinted that these networks might be able to learn.
Which leads us right to Donald Hebb, 1949, and his learning rule.
Ah, Hebbian learning, yes. Still hugely influential.
The whole neurons that fire together, wire together idea.
That's the gist of it. It's a simple concept. If two connected neurons are acting around the same time, the connection between them gets stronger. But it provided a plausible mechanism for how learning could actually happen in these networks. Its influence is, it's hard to overstate.
Okay, so fast forward just a bit. 1956, the Dartmouth Workshop. This sounds like a big deal, often called the birthplace of AI.
That's the common view, yes. It's where the term artificial intelligence was really adopted and the field got its start as a formal academic discipline.
And the vibe there was Pretty optimistic.
Incredibly optimistic. The proposal for the workshop famously stated this belief that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it.
That's
Very. It reflects the excitement, the feeling that they were on the cusp of something huge.
And out of that came some core ideas, like the physical symbol system hypothesis. What's that about?
Essentially, it's the idea that intelligence boils down to manipulating symbols according to rules. Like, thinking is a form of computation over symbolic representations. Words, numbers, logical statements, those are symbols.
Got it. And we started seeing actual AI programs emerge then, too.
We did some really impressive early work, like Herbert Gellinter's geometry theorem prover.
Moving geometry theorems?
Yeah, theorems that could actually be quite challenging for people. And then there was Arthur Samuel's work on checkers. That one really captured attention.
The checkers program. Because this wasn't just playing, right? It learned.
Exactly. That was the key thing. It learned to play checkers better than Samuel himself.
How?
Through what we now call reinforcement learning. Basically trial and error. It played games, saw what worked, adjusted its strategy, and got progressively better over time.
And that directly challenged the old saying, didn't it? That computers can only do what you program them to do.
Absolutely. Here was a machine improving beyond its initial programming, learning from experience.
Yeah.
And Samuel actually showed it on TV back in '56.
Wow, really?
Yeah, which had a pretty big impact. It made the idea of machine learning much more concrete for people.
Okay.
And you can draw a direct line from Samuel's work to later game-playing successes, like TD Jammin' and Backgammon.
Right.
And, much more recently, AlphaGo stunning the world by beating the Go champion. It all builds on that core idea. Machines can learn, sometimes even better than us, in specific areas.
So yeah, we've definitely covered some serious ground here. Going back to our mission exploring knowledge, reasoning, learning, interaction in these sources.
Yeah.
It's amazing to see the path from like the Turing test's philosophical sidestep through the formal logic and the first neuron model
McCulloch-Pitts have.
to those first learning programs like Samuel's. These foundational pieces really set the stage for, well, everything AI is today.
It's fascinating how these different threads, the logical, the probabilistic, the learning-based approaches, they didn't just develop separately. They've constantly interacted and influenced each other.
Yeah, building on each other.
Exactly. The history isn't strictly linear. It's more like a braid.
Which does make you wonder, doesn't it? You look at that path from those early rule-based systems and logic through probability, now to deep learning. What's the next fundamental shift going to be?
Good question. What does the next generation of AI look like?
And what totally unexpected things might machines become capable of as we keep pushing? Definitely something for you, our listener, to think about. Thanks for joining us on this deep dive.